For this exercise, I want to show you how to find the eigenvector of this matrix and the eigenvalues, and then how to find the eigenvectors of the inverse of this matrix and its eigenvalues without finding the inverse. Okay, so at first, let us find the eigenvalues. Let us remember that if we have a matrix A and we multiply it by some vector v, and that results in just a stretching of that vector without knocking it off its span, we have this expression. And this is basically the eigenvalue problem. We want to find a vector that, when applied a transformation A, gives that same vector just scaled by a scalar. And we want to make the right-hand side matrix multiplication like the left. So we add the identity matrix, which really doesn't change much because the identity matrix is the equivalent of 1 in the matrix world. Then we subtract lambda I v to both sides, and we get a v minus lambda I v equals the 0 vector. Now we can factor out a v vector, and we get the following. Excuse me. So we're not interested in the trivial solution, which would be if v were to be the 0 vector. We're interested in how to make that expression the 0 vector with the other term, and that would be if the determinant of that term is equal to 0. So why don't we find the determinant of this term? Well, the determinant of this term is going to result into being, let's see, we have our A5115 minus lambda and the identity matrix 1001. And then we want to find the determinant of this. So I'll put this and I'll say it indicated like this. Well, okay, so this is going to simplify to the determinant of 5115 minus lambda 0, 0, lambda. And then if I execute the subtraction, then I can write the determinant like this. And I can have 5 minus lambda, 1, 1, and 5 minus lambda. Just like this. Now, to find the determinant, I can factor out a negative sign, and I will. So I'll get lambda minus 5, and I'll factor out a negative sign from this as well. The two negative signs cancel out, and then I have this, which I can develop into lambda squared minus 10 lambda plus 25 minus 1. And that is equal to lambda squared minus 10 lambda plus 24. Now, can you factor this? I can think of two numbers, -8 and -2. Well, that would be factorable like this. So the only way this expression can be 0 is if one of the lambda is equal to 8, if the lambda is equal to 8, or if lambda is equal to 2. So we have these two. Now, we have found the eigenvalues. Now, to find the eigenvectors, we plug the eigenvalue back here, and we solve for v. So, plugging back what that whole expression in parentheses was, for lambda 1, it was 5 minus 8, 1 and 1, and 5 minus 8. And then it was multiplied by a vector v, which we can say has coordinate x and y, and those all had to be equal to the 0 vector. So, this is the same thing as -3 times x plus y equals 0. And if we are to do the second part, it's going to be x minus 3y equals 0. Okay, so now we see, perhaps we see something interesting happening. So let's see we can say from this top equation that y is equal to 3x. From this bottom equation, we can say that y is equal to 1/3 x. So it kind of looks like this system is inconsistent unless I made a mistake, which could be. Let's see. Yes, right here, to get 24, you'd have to multiply 6 and 4. 8 and 2 would give us 16. So this would be 6 and 4. So these would be 6 and 4. Now, I'll go with the first value, with the value of 6. And what we get is x plus y here. And on the top, we get negative x plus y. The bottom here, we actually get a -1. So the coefficient of y, it becomes negative. And so now this is consistent. And we have the same equation, basically. We have that x is equal to y, which means that for lambda 1 of 6, we get that the vector, corresponding eigenvector, is a 1, 1. Or in other words, we're saying let x be equal to t, then y is also equal to t. So here we have a vector tt, and we can assign any value, which includes 1, 1. And that gives us the first eigenvalue. We'll do the same thing for the second eigenvalue, which is 4. So 5 minus 4 is 1, and here we have 1. 1, 5 minus 4 is 1. And then we have to solve this same system. Now notice how we have the same equation at the top and at the bottom. So we really only need one, x plus y equals 0, which means that x is the negative of y. And if we let x be t, then y is going to be negative t. So for lambda 2 of 4, our vector, eigenvector, is going to be t and negative t, for which we can choose any value. So this right here ends up being our answer. I hope you understood everything, and I hope you try to do some of it yourself, and I'll see you next time.